Welcome grade 8 students. This is teacher Christine, your science teacher for today. Before we start with our lesson, please prepare the following materials: your textbook, a ball, a pencil, glass with water, and a mirror. So for today, we will be discussing about the interaction of waves. At the end of the lesson, you have to know the following words: reflection, refraction, diffraction, interference, constructive interference, destructive interference, standing wave, node, antinode, and resonance. Waves can change direction. Waves change direction by three processes, namely reflection, refraction, and diffraction. Light waves differ from sound and water waves because light travels through an empty space. The first interaction of wave is called reflection. Reflection occurs when a wave strikes an object and bounces off of it. We can simply show reflection when we throw a ball in a wall. Obviously, when you do this, the ball will bounce back to you. All types of waves, including sound, water, and light waves, can be reflected. Another way of showing reflection is by using a mirror. You can get your mirror and observe what happens. How does the reflection of light allow you to see yourself in the mirror? It happens in two steps. First, light strikes your face and bounces off. Then, the light reflected of your face strikes the mirror and is reflected into your eyes. The law of reflection. The beam striking the mirror is called the beam of incident. So as you can see here in the picture, this is the beam of incident. The beam that bounces off the mirror is called the reflected beam. And in this picture, this is the reflected beam. The line drawn perpendicular to the surface of the mirror is called the normal. So in this picture, you can see the normal here. So this is the line perpendicular to the surface. According to the law of reflection, the angle formed by the incident beam and the normal is the angle of incidence. So in this picture, this one is the angle of incidence. The angle formed by the reflected beam and the normal is the angle of reflection. And this one is the angle of reflection. According to the law of reflection, the angle of incidence is equal to the angle of reflection. So you can see here in the picture, this is the angle of incidence. So for example, let's say you were able to form an angle of 45 degrees in the angle of incidence. So that means the measurement of the angle in the angle of reflection should be also 45 degrees. All reflected waves obey this law. To summarize, look at this picture. So you can see this one is letter A. This is the incoming wave, a wave moving toward the surface at an angle. So this is the surface. And this is B. This is the angle of incidence, the angle between the incoming wave and the normal. And this one, letter C, is the normal. It is a line perpendicular to the surface at the point where reflection occurs. And this is letter D, which is called the angle of reflection, the angle between the reflected wave and the normal. And lastly, this is letter E, which is called the reflected wave, a wave bouncing off the surface at an angle. So, where can you usually see reflections? You can see reflections in mirrors, windows, shiny metal surfaces, and water. Are light waves the only waves that are reflected when they hit a surface that they cannot pass through? No, all waves are reflected whenever they hit a surface they can pass through. So what is the term for a reflection of sound wave? We call it echo. So if someone is shouting, his voice hits the wall and bounces back, producing an echo. The second interaction of wave is called refraction. If the wave is traveling at an angle when it passes from one medium to another, it changes direction or bends as it changes speed. When a wave passes from one medium to another, such as when a light wave passes from air to water, it changes speed. So when you say refraction, it is simply the bending of a wave caused by a change in its speed as it moves from one medium to another. In this picture, you can see a pencil. It's slightly bended. Okay? Why? What's the reason of this? It's because the pencil passes through two mediums, namely the air here and the water. So as it passes through medium, the speed of light changes, causing the wave to bend. Refraction of light in water. Light waves travel slower in water than in air. This causes light waves to change direction when they move from water to air or air to water. When light waves travel from air to water, they slow down and bend toward the normal. On the other hand, when light waves travel from water to air, they speed up and bend away from the normal. The third interaction of wave is called diffraction. Diffraction occurs when an object causes a wave to change direction and bend around it. Diffraction and refraction both cause waves to bend. The difference is that refraction occurs when waves pass through an object, while diffraction occurs when waves pass around an object. When wave strikes an object, several things can happen. The waves can bounce off or be reflected. If the object is transparent, light waves can be refracted as they pass through it. Waves also can behave another way when they strike an object. The waves can bend around the object. Waves also can be diffracted when they pass through a narrow opening. After they pass through the opening, the waves spread out, as you can see in this picture. Interference. Have you ever seen soccer balls collide? The balls bounce off each other because they cannot be in the same place at the same time. Surprisingly, this is not true of waves. Unlike two balls, two waves can overlap when they meet. Interference is the interaction between waves that meet. Interference is responsible for the iridescent colors seen in oil films, soap bubbles, and the feathers of some birds, like the common grackle. The structure of the bird's feather creates the interference. The bright colors are only seen at specific angles of reflection. There are two types of interference, namely constructive and destructive interference. Interference in which waves combine to form a wave with a larger amplitude than any individual wave's amplitude is called constructive interference. The diagram labeled A shows two identical waves with the same amplitude and the same wavelength, traveling in the same direction at the same time. If the two waves travel along the same path at the same time, they will behave as one. You can think of constructive interference as waves helping each other or adding their energies. So we can simply say that in constructive interference, the waves add together. What will the combined wave look like? So you can see in this picture, the crest of the first wave will occur at the same place as the crest of the second wave. The energy from the two waves will combine together. Thus, the amplitude of the new wave will be twice the amplitude of either of the original waves. When the crests of two waves overlap, they make a higher crest. If two troughs overlap, they make a deeper trough. In both cases, the amplitude of the combined crests or troughs increases. In this picture, the amplitude of the new wave that forms is equal to the sum of the amplitudes of the original waves. When the crests of one wave align with the troughs of another, they cancel each other out. Look at the picture in letter B. In letter C, if one wave travels a little behind the other, They combine both constructively and destructively at different places. The second type of interference is called destructive interference. In destructive interference, the waves subtract from each other as they overlap. Destructive interference can occur when the crest of one wave overlaps the trough of another wave. If the crest has a larger amplitude than the trough of the other wave, the crest wins, and part of it remains. If the original trough had a larger amplitude than the crest of the other wave, the result is a trough. If a crest and a trough have equal amplitudes, they will completely cancel. The best example of destructive interference is a use of a noise-canceling headphones. Destructive interference is used in noise-canceling headphones to block out distracting noises in a listener's surroundings. How do standing waves form? If you tie a rope to a doorknob and shake the free end, waves will travel down the rope, reflect at the end, and come back. The reflected waves will meet the incoming waves and interference occurs. The reflected waves will collide with the incoming waves. When the waves meet, interference occurs. If the incoming wave and the reflected wave combine at the right places, the combined wave appears to be standing still. A standing wave is a wave that appears to stand in one place even though it is really two waves interfering as they pass through each other. If you make a standing wave on a rope, the wave looks as though it is standing still. In a standing wave, destructive interference produces points with zero amplitude called nodes. The nodes are always evenly spaced along the wave. At points in the standing wave where constructive interference occurs, the amplitude is greater than zero. Points of maximum amplitude in a standing wave are called antinodes. The antinodes always occur halfway between two nodes. So you can see in this picture, this is where you can find the nodes. We can say that the amplitude here is zero. And this is where you can see the antinode. This is the point where the maximum amplitude is located. Resonance. Have you ever pushed a child in a swing? At first, the swing is difficult to push. But once it is going, you need only a gentle push to keep it going. This is because the swing has a natural frequency. Even small pushes that are in rhythm with the swing's frequency produce large increases in the swing's amplitude. When an object is vibrating at a certain frequency, it takes very little energy to maintain or increase the amplitude of the wave. Most objects have a natural frequency of vibration. Their particles vibrate naturally at a certain frequency. Resonance occurs when vibrations traveling through an object match the object's natural frequency. If vibration of the same frequency are added, the amplitude of the object's vibration increases. If an object is not very flexible, resonance can cause it to shatter. For this reason, marching troops are told to break step as they cross a bridge. If they all march across the bridge in a perfect step, it is possible that the pounding could match the natural frequency of the bridge. The increased vibration could cause the bridge to collapse. The Tacoma Narrows Bridge or Galloping Gertie may have collapsed because of resonance. Storm winds are said to have resonated with the natural frequency of the bridge. These caused the amplitude of the bridge's way to increase until the bridge collapsed. You can see the result of the collapse in this picture. Thank you so much for listening. That's all for today. Please do refer in the weekly plan for your daily tasks that you have to accomplish at the end of the week. Again, thank you so much.